Okay, so I want to continue the conversation talking about acid-catalyzed hydration. Right, in the previous video, we sort of learned the basic reaction, right? Break the pi bond, add H and OH, follow Markovnikov's rule, right? Remember, Markovnikov's rule is really about forming the most stable carbocation. But in this video, right, I really want to talk about rearrangements, all right? So it turns out with this reaction, we can have rearrangements. So I want to show you an example on what that looks like, okay? The key in this reaction is that we want to form the most stable carbocation that we can. So in these two examples that we did, right, if you work through the mechanism, you'd form a tertiary carbocation, you'd form a tertiary carbocation. So that's the most stable carbocation we can. But I can give you examples where that's not the case, and that's when a rearrangement can and will occur. Okay, so here's an alkene. Okay, I'm going to, again, treat this with some dilute acid, right? So in this case, we'll say we're using dilute H3PO4, okay? And now we have to kind of figure out what the product is. So in this example, I'm going to work through the mechanism first, right? And then determine what the product is. So again, when we have H3PO4 dilute, that's really forming this hydronium ion species, right? That's forming H3O plus, which really, to simplify, is giving you H plus water, right? And that makes it easier to do our mechanism. So let's look at our first step. Again, we're going to protonate the pi bond of the alkene. So the pi bond will break and attack that proton. We're going to be adding a hydrogen to one side. Okay, we follow Markovnikov's rule. So we're going to be adding the hydrogen to the side where there's more hydrogens. All right, so let me just draw the hydrogens in here we have. So we're going to be adding this hydrogen. There's the new bond in blue, right? Now we see that this sp2 carbon here is going to have a plus charge, right? So in our first step, this is the most stable carbocation we can form. And it turns out that this is a secondary carbocation because this carbon in green is attached to 2 carbons and 1 hydrogen, all right? That's a secondary carbocation. So when we form a secondary carbocation, we have to think, I can form a more stable, right? A tertiary carbocation is more stable than that. So what I really want to do is sort of examine the carbon next to the sp2 carbon here. Is there any way I can rearrange an atom to form a carbocation that's more stable? And obviously in this example, that's what we're going to do. So I want to show you that. So what I'm going to do with this carbon is I'm going to add in our hydrogen, right? We know this hydrogen is here. Carbon always has to make 4 bonds. So this is the key for the next step. What can happen and what does happen is this hydrogen connected to this carbon can rearrange. This carbon-hydrogen bond can break and shift over there, shifting the hydrogen over to that carbon, right? So our first step was a protonate. Now what we've done is a rearrangement. So if we look at this, we still have our same carbon backbone. There's the original hydrogen in black, right? 2 more hydrogens. The first blue we added in our first step. And now this orange hydrogen has shifted over to this green carbon here. So this green carbon, now that carbon has 4 bonds, so it's neutral, right? But we look at the carbon in red to the left. Because I've moved this hydrogen over, that carbon only has 3 bonds. So what does that mean? It doesn't have a full octet. That carbon is a carbocation. And what type of carbon is this? What type of carbocation? We've now done this to form a tertiary carbocation, right? This carbocation, a tertiary, is more stable than a secondary. That's why this rearrangement occurs. We've now formed a more stable carbocation. And this is the most stable carbocation we can form. So now we simply finish the mechanism. Our water, a lone pair on the O, can attack that carbon atom, right? Remember, water is our nucleophile, our carbocation is our electrophile. That can attack that carbon there on the left. Forming a new bond from that carbon to our oxygen. This O was connected to two H's and had two lone pairs. One of those lone pairs is forming the new bond. So we've gone from a bond to a lone pair. That O is still connected to two hydrogens and still has a lone pair associated with it. Now this oxygen only has 5 valence electrons around it. Therefore, this oxygen now has a positive charge. What do we do to finish the mechanism, right? So that was an attack step. To finish the mechanism, we're going to deprotonate the H, keeping the electrons. So I'm going to take H2O, 2 lone pairs. This lone pair, one of these lone pairs is going to form a new bond to the H. That bond is going to become a lone pair on the O. So if we look what we have here, we now have our carbons, another carbon here, and we have our single bond to an OH. And that OH now has 2 lone pairs. And this is what our final product will be. Okay? So let's just review the mechanism again, right? The first step, the pi bond is going to protonate the H+, adding it, following Markovnikov's rule, adding it to the carbon where there's more hydrogens, forming a secondary carbocation. Because this is a secondary carbocation, we now have to look at the adjacent carbon. We can now shift over a hydrogen to form a tertiary carbocation. This is now the most stable carbocation we can form. So our water molecule can now attack, and then we can deprotonate using these arrows to get our final product. And this is a rearrangement that we can form. All right? So what we can see is we're really shifting over a hydrogen. This isn't the only thing that can shift over. Okay, we can actually shift over a whole methyl, right? So if I look at an example like this, it's going to be very similar. Now I have 2 methyl groups here. If I treat this with H3O+, we're going to go through exactly the same mechanism. You'll protonate, you'll rearrange, you'll attack, and you'll deprotonate. But now I'm not going to be shifting over a hydrogen. I'm going to be shifting over one of these methyls. So our skeleton structure is going to change. That methyl will shift over here. We'll still have one methyl here, and now our alcohol is going to form over there, right? So I'd encourage you to try this mechanism and post it to the discussion board, all right? So in this example, we've really shifted over a methyl. So this is a methyl shift, okay?